Good afternoon, everyone. Thank you for the introduction from Mr. Chairman. So this is Wataru Matsunaga. I'm assistant professor at Kyoto University in Japan. So the title of my presentation is Engineering of Fracture Toughness of Amorphous Silica by Excess Electrons and Holes. This is the outline to today's presentation. First of all, let me explain the background. Generally, mechanical properties are specific to each materials. However, look at these movies. This is a bending deformation, this is a bending clip experiment on silicon nanocantilevers with under electric beam irradiation. This result shows a large deformation and it finally contacts the substrate without breaking, in spite of being brittle materials. So why does this phenomenon occurs? When the solid materials are irradiated with EBs, excess electrons and holes are injected into materials. The fundamental process of the plastic deformation and fracture ultimately involves breaking of atomic bonds. Therefore, excess electrons and holes influence the strength of atomic bonds. When materials are irradiated with EBs, a large number of excess electrons and holes are injected into materials. For semiconductors, when EB irradiation is stopped, it becomes electrically neutral due to its high electrical conductivity. As a result, mechanical properties change only under EB irradiation. On the other hand, for insulators, when EB irradiation is stopped, excess electrons and holes remain as electrostatic charges. Therefore, mechanical properties may continue to change after EB irradiation. So this suggests EB irradiation potentially implies permanent alteration of mechanical properties. We control mechanical properties by injecting and removing of excess electrons and holes. We injecting excess electrons holes by EB irradiation at target local locations. This approach is expected to lighten the strengths. In addition, we remove the excess electrons and holes by modifying the surrounding environment, like this. This process is anticipated to erasing the strengths. However, no studies have demonstrated the lighting and erasing of strengths due to its electronic effect. So the objective of this study is engineering of fracture toughness of amorphous silica by injection and removal of excess electrons and holes. In order to achieve this objective, we apply these approaches. First, the material is synthetic fused silica. This is amorphous silica. Second, EB irradiation is applied to inject excess electrons and holes. And injected excess electrons and holes are removed by exposuring to atmospheric conditions and annealing. Finally, micropillar splitting tests were conducted. Next, let me explain the experimental procedures. This is a flow diagram of the experiment. Firstly, micropillar specimens were fabricated by focused ion beam machining, and they were called non-charged specimens. Some of the non-charged specimens were EB irradiated in the scanning electron microscope, and they were called charged specimens. Some of the charged specimens were exposed to the atmospheric condition, and they were called vented specimens. Some of the vented specimens were annealed, and they were called annealed specimens. So fracture toughness tests in the SEM were conducted on non-charged, charged, vented, and annealed specimens. Next, I will explain the charged and charge removed conditions. Regarding charged conditions, acceleration voltage was 5 kilovolt, irradiation current was 0.1 microampere, and angle of incidence was 70 degrees. Secondary electron emission rate can be estimated significantly larger than 1. So this experimental condition realized whole-rich state. Next, regarding the charge removing conditions of vented specimens, charged specimens were placed in the desiccator for approximately 5 days under vacuum. For annealed specimens, charged specimens were annealed at 100 degrees Celsius. Next, let me explain the fracture toughness testing conditions. In this study, we applied micropillar splitting test. In the previous study, fracture toughness Kc can be calculated by using this equation. In this equation, R is the radius of microspecimen. In this study, average value of top and bottom radius 2.3 micrometer was applied. So gamma is a dangerous number related to Young's modulus and hardness of materials and the shape of the tip of the indenter. In the previous research, when the cube corner indenter was applied to the synthetic fused silica, this value was 0.49, and the same value was used in this study. So PC is the fracture load. We experimentally measure load just prior to unstable fracture due to crack propagation. Okay, let's start experimental results. This is the load displacement relationships in all types of specimens. This result shows that the shape of the loading curves was similar in all types of specimens. Specifically, P increased monotonically with D, followed by a rapid increase in D, and this is onset of an unstable fracture. So this is the cumulative probability of fracture toughness of non-charged specimens. According to this result, median of Kc of non-charged specimen is this value. This is the cumulative probability of fracture toughness of charged specimens. A median of Kc of charged specimen was this value, and Kc increases approximately 2.4 times larger compared to that of non-charged specimens. So, writing the strength is realized. So this is the cumulative probability of fracture toughness of vented specimens. A median of Kc of vented specimen is this value, and Kc is between non-charged and charged specimens. This result denoted that fracture toughness remained high, although the results were obtained more than 5 days after EV irradiation. So this result suggests that permanent alteration is realized. So this is a cumulative probability of fracture toughness of annealed specimens. A median of Kc annealed specimen is this value, and Kc is between non-charged and vented specimens. This result denoted that fracture toughness restored by ambient environment. So releasing the return strength is realized. Okay, let's start discussions. In the previous research, first principle calculation on the effect of excess electrons and holes on the ideal strength of single crystal silicon was calculated. This is the result of strain stress curve of the single crystal silicon with different hole densities. According to these results, ideal tensile strength increased by hole doping, and this is qualitatively consistent with the experimental results. However, in this study, the fracture toughness increases dramatically. This is because of the crystal structure of amorphous silica. Amorphous silica has numerous point defects, and point defects can act as a trapping sites for electrons and holes. Therefore, UV irradiation may have contributed to dramatic increase in fracture toughness by trapping excess electrons and holes in numerous point defects. Previous research also analyzed the change of the tensile strength and the shear strength of in the several materials with different holes and electron densities by using first principle calculations. The left figure is the tensile strength and the right figure is the shear strength. So according to these results, introduction of holes increases tensile strength and decreases shear strength. Therefore, partial transition of the fracture mechanism from tensile-dominated brittle fracture to shear-dominated ductile fracture. Lastly, let me discuss about the permanent alteration of the fracture toughness. In the previous research, electrostatic charges remains for approximately 2 days. Therefore, excess electrons and holes remain as electrostatic charges, and bented specimens denoted that the high fracture toughness even after 5 days. Finally, I will conclude my presentation. The objective of study is engineering of fracture toughness of amorphous silica by injection and removal of excess electrons and holes. In order to achieve this objective, we conducted micropillar splitting tests on non-charged, charged, bented, and annealed specimens, and these results were obtained. First, the fracture toughness of charged specimen was approximately 2.4 times larger than that of the non-charged specimens, lighting strength. Next, exposure of the charged specimen to air and heat lead to decrease in fracture toughness, albeit without complete restoration to pre-charging level. This means erasing the return stress. These results suggest that the possibility of engineering of fracture toughness of amorphous silica by injection and removal of excess electrons and holes. So this work was supported by JSPS Kakenshi. Thank you for your attention.